Imagine a shortcut, a cosmic tunnel connecting two distant points in the universe. This is the essence of an Einstein-Rosen bridge, better known as a wormhole. Wormholes, if they exist, could revolutionize our understanding of space and time, offering potential for faster-than-light travel and journeys to distant galaxies. The concept of a wormhole arises from Albert Einstein's theory of general relativity. This theory, a cornerstone of modern physics, describes gravity not as a force but as a curvature of space-time itself. Imagine a bowling ball placed on a trampoline causing it to sag. This is akin to how massive objects warp the fabric of space-time. Now, imagine folding that trampoline in half, bringing two distant points close together. A wormhole in theory would function similarly, creating a bridge through the fabric of space-time. This bridge could potentially connect two black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape. The idea of traversing vast cosmic distances through these space-time tunnels is tantalizing. However, the existence of wormholes remains theoretical, and their stability and traversability are still open questions. To grasp the concept of wormholes, we must first understand the revolutionary ideas behind Einstein's general relativity. Prior to Einstein, gravity was understood through Isaac Newton's framework, where it acted as a force between objects with mass. Einstein, however, proposed a radical shift in our understanding. He envisioned space-time as a four-dimensional fabric, a unified entity of space and time. Massive objects like stars and planets warp and curve this fabric, much like a ball placed on a stretched sheet. This curvature, Einstein argued, is what we perceive as gravity. Imagine rolling a marble across this stretched sheet. Its path curves as it approaches the bowling ball, not because of a direct force, but because the ball has distorted the sheet itself. Similarly, objects in space follow curved paths due to the warping of space-time by massive objects. This revolutionary concept, published in 1915, not only explained the anomalies in Mercury's orbit that had puzzled physicists for decades, but also predicted the bending of starlight by the sun's gravity, later confirmed by observations during a solar eclipse in 1919. This confirmation catapulted Einstein to global fame and solidified general relativity as a cornerstone of modern physics. At the heart of general relativity lie the Einstein field equations, a set of 10 complex equations that describe the interaction between matter and energy and the curvature of spacetime. These equations are the mathematical language of gravity, revealing how the universe's fabric bends and warps in the presence of mass and energy. While the equations themselves are highly complex, their essence can be understood through analogy. Imagine a trampoline again, this time with a grid drawn on its surface. As you place heavier objects on the trampoline, the grid lines distort, representing the curvature of spacetime. The Einstein field equations essentially describe how the stretching and curving of these grid lines representing spacetime are directly related to the mass and energy present. The more massive the object, the greater the distortion, and hence the stronger the gravitational pull. These equations, however, do more than just describe gravity as we know it. Hidden within their complex mathematics are solutions that point to the possibility of wormholes, these theoretical tunnels through spacetime. Visualizing a wormhole can be challenging, as it involves imagining a tunnel through a four-dimensional fabric. However, analogies can help us grasp this mind-bending concept. One common analogy is to picture spacetime as a sheet of paper. Draw two dots on this sheet, representing two distant points in space. Normally, traveling between these points would require traversing the entire distance across the paper. Now, fold the paper in half, bringing the two dots close together. If you could poke a hole through the folded paper, you'd create a shortcut between the 2 points, much like a wormhole through spacetime. Another helpful visualization involves imagining an ant crawling on the surface of an apple. The ant, constrained to the apple's surface, represents us bound by spacetime. A wormhole would be like a tunnel bored through the apple, allowing the ant to travel instantly between two distant points on the surface. These analogies, while simplifications, provide a glimpse into the potential of wormholes as shortcuts through the vast cosmic distances of our universe. Section 5. A wrinkle in time. The concept of wormholes, though rooted in Einstein's equations, was first explored in depth by physicist Ludwig Flamm in 1916. Flamm, while studying solutions to Einstein's field equations, realized they allowed for the possibility of a white hole, a hypothetical region of spacetime where matter and energy could only exit, as opposed to a black hole where they can only enter. It was Einstein himself, along with physicist Nathan Rosen, who further developed this concept in 1935. They explored the possibility of connecting a black hole and a white hole, forming a bridge through spacetime, the Einstein-Rosen bridge, or wormhole. Their work suggested that a wormhole could act as a tunnel, connecting two different regions of spacetime, potentially even different universes. This opened up a Pandora's box of possibilities, from faster-than-light travel to journeys through time itself. However, Einstein and Rosen's wormholes were highly unstable. They would collapse too quickly for anything to travel through them, rendering them impassable. Section 6. Matter and Energy, the Architects of Spacetime. While Einstein's equations predicted the possibility of wormholes, they also highlighted a significant challenge: their instability. For a wormhole to remain open and traversable, it would require a peculiar form of energy known as exotic matter. This exotic matter would possess negative mass-energy density, essentially meaning it would have less than nothing in terms of energy. While this might sound like science fiction, the concept of negative energy density is not entirely foreign to physics. For instance, the Casimir effect, a phenomenon observed in quantum mechanics, demonstrates the existence of negative energy densities in certain configurations. This exotic matter, if it exists, would act as a cosmic scaffolding, preventing the wormhole from collapsing under its own gravity. It would exert a negative pressure, pushing the walls of the wormhole outward and keeping it stable. However, the existence of exotic matter in sufficient quantities to prop open a wormhole remains highly speculative. Its properties and behavior are still largely theoretical, making the creation and stabilization of wormholes a daunting challenge. Section 7. Through the Looking Glass. The allure of wormholes extends beyond their potential for interstellar travel. Some physicists speculate that wormholes could even act as gateways through time, allowing for journeys into the past or future. Imagine a wormhole connecting 2 points in time, much like it could connect 2 points in space. Theoretically, entering one end of the wormhole could transport you to a different moment in time, effectively turning the wormhole into a time machine. However, the concept of time travel is fraught with paradoxes and inconsistencies. The grandfather paradox, for instance, where a time traveler accidentally kills their grandfather in the past, creating a logical contradiction, highlights the complexities and potential dangers of manipulating time. While the idea of wormholes as time machines remains purely speculative, it continues to capture the imagination and fuel debate among physicists and science fiction enthusiasts alike. Section 8. Dreams of Interstellar Travel. The vast distances between stars and galaxies pose a significant hurdle for space exploration. Even with the fastest spacecraft imaginable, journeys to other star systems would take thousands, if not millions of years. Wormholes, if they exist and are traversable, could offer a revolutionary solution. Imagine stepping through a wormhole and emerging light years away, bypassing the vast cosmic distances and reaching your destination in a fraction of the time. Such a feat, if possible, would revolutionize space exploration, opening up the cosmos to human exploration and potentially enabling contact with extraterrestrial civilizations. However, the challenges of creating, stabilizing, and navigating wormholes are immense. The technological requirements for such an endeavor are far beyond our current capabilities. Despite these challenges, the dream of interstellar travel through wormholes continues to inspire scientists and fuel our imaginations, pushing the boundaries of what we believe is possible. Section 9. The Universe's Unanswered Questions. Wormholes, these theoretical tunnels through space-time, remain one of the most intriguing and mind-boggling predictions of modern physics. While their existence is still uncertain, the possibility of their existence alone speaks volumes about the universe's potential for strange and wonderful phenomena. The search for wormholes is, in many ways, a search for answers to some of the universe's most fundamental questions. Can we truly bend and warp the fabric of space-time? Can we unlock the secrets of exotic matter and harness its power? Can we conquer the vast cosmic distances and unlock the mysteries of the universe? As we continue to explore the cosmos and delve deeper into the intricacies of Einstein's equations, we may one day find answers to these questions and unlock the true nature of these cosmic shortcuts, these bridges through space and time. Until then, wormholes remain a tantalizing enigma, a testament to the boundless possibilities that lie hidden within the fabric of our universe.